This question is taken from Cape Mathematics Made Simple, Unit 2 by V.J. Mahavir. The question is page 350, exercise 11b, number 1. We're required to solve the second order differential equation y double prime minus 4y prime minus 5y is equal to 3 times e to the 2x. This is what we call a non-homogeneous differential equation. It's non-homogeneous because on the right-hand side, we have a non-zero term. So the first step is to write down what we call the associated homogeneous equation. And to get that, we simply replace the term on the right-hand side by 0. So the associated homogeneous equation would be y double prime minus 4 times y prime minus 5y is equal to 0. This is the associated homogeneous equation. So it's the non-homogeneous equation rewritten with a 0 on the right hand side instead of the 3 times e to the 2x term. The second step would be to write down what we call the auxiliary or characteristic equation. And usually we use either m, p, or r as the variable. So we rewrite the associated homogeneous equation like this. So if I use m squared, because it's the second derivative, so m to the power 2 minus 4 times y prime is the first derivative, so I'll write that as m minus 5 is equal to 0. So the characteristic or auxiliary equation is actually a quadratic equation that we must solve. Now, you would recall from your CSEC studies that a quadratic equation can fall into one of 3 cases. We can have 2 real and distinct roots, or 2 real and equal roots, or 2 complex roots, or what we say imaginary roots. In this case, it would be easy to see that this can factorize as m minus 5 by m plus 1 is equal to 0, and therefore the roots are 5 or minus 1. As such, our complementary solution, which we denote as y sub c, is equal to c1 e to the 5x plus c2 e to the minus x. And I hope you can see where the 5 and minus 1 came from. Those were the roots of the auxiliary equation. So we found those roots to be 5 and minus 1. And therefore, they would be the coefficient of x, right? E to the power 5x and e to the power of minus 1x. Now, what is important is that e to the 5x and e to the minus x are linearly independent. So if we had gotten a repeated root of, say, 5 and 5, then it would not be correct for the complementary solution to be c1 e to the 5x plus c2 e to the 5x. These 2 terms must be linearly independent. In other words, they must come from a different family of curves. So if we have e to the 5x here and e to the 5x here, we would have had to multiply this entire term by x to have made them linearly independent. But we don't need to worry about that complication here because 5 and minus 1 are 2 real and distinct roots. So the c1 e to the 5x and c2 e to the minus x terms will suffice because e to the 5x and e to the minus 1x are linearly independent. So this will be our complementary solution. The second part of this will require us to find the particular solution, y sub p. Now y sub p we now look at the right-hand side of the original non-homogeneous equation, and we see it's 3 times e to the 2x. So my particular solution should be of the form a times e to the 2x. You see e to the 2x. I got that from the right-hand side. This term is 3 times e to the 2x. So I now have a times e to the 2x. A is what we call an undetermined coefficient, and I'm going to have to solve for a. Now, please note that C1 and C2, we cannot determine those values unless we were given boundary conditions, and we weren't at the start of this problem. So C1 and C2 will remain unknown even at the end when we get the final solution. But a, the undetermined coefficient, that is something that we can find. Now, we also have to check that y sub p and y sub c, all of these terms are linearly independent of each other, and that is the case here because y sub p has an e to the 2x term, and that's going to be linearly independent of both e to the 5x and e to the minus x. So the next thing to do, we are going to substitute our particular solution into the original non-homogeneous equation. So we have a y. We have to get y prime and y double prime in order to substitute into the original equation. So y prime, yp prime would be equal to, and I now have to differentiate, a times e to the 2x. That would give me 2a by e to the 2x, and y double prime p would be 4a times e to the 2x, and I will now substitute into the original non-homogeneous equation. So where I see y double prime, I'm going to put 4 times a e to the 2x minus 4 times y prime, and y prime is 2a e to the 2x. I got that from here. Minus 5y, and y is a e to the 2x. And I'm going to put that equal to 3 times e to the 2x. I got that from the original non-homogeneous equation, so I'm substituting into that. What I'm going to do now is simplify the left-hand side and equate it to the right-hand side to determine a. So I'm going to get 4a e to the 2x minus 8a by e to the 2x minus 5a by e to the 2x equals 3 times e to the 2x. And the left-hand side will simplify as 4a minus 8a is minus 4a minus 5a. That's minus 9a e to the 2x is equal to 3e to the 2x. And it should be easy to see here if we compare coefficients of e to the 2x, we can solve for a. Comparing e to the 2x coefficients, minus 9a would be equal to 3. Therefore, a is equal to 3 over minus 9. That's minus 1/3. Therefore, my y sub p, I now know what a is. It's minus 1/3. So y sub p will be minus 1/3 e to the 2x. And finally, my solution, y is equal to y sub c plus y sub p. I'm going to combine the complementary and particular solutions. You'll recall the complementary solution we found up here after we got the roots to the auxiliary equation. And that was c1 e to the 5x plus c2 e to the minus x And we're now going to combine that with our particular solution, minus 1/3 e to the 2x. Good, and that is going to simplify to, I'm going to write it over here, y is equal to c1 e to the 5x plus c2 e to the minus x minus 1/3 e to the 2x, and that's my final solution. And as you can see, every term is linearly independent, right? Each term is linearly independent of every other term. So we have 3 linearly independent terms, and that is our final solution.